This presentation addresses the topics of atoms, molar mass, Avogadro's number, and empirical formulas. Let me just say that an accurate description of the atom is beyond the scope of this presentation. For the curious mind, there will be other videos. A disclaimer has been added to this slide to reflect the fact that most images of atoms you might have seen in textbooks are just artistic renditions meant to convey certain information. The accurate picture of the atom is just too complex to put in one picture. The concept of atoms and molecules is relatively new in the scientific community. Some people might say, the ancient Greeks discovered atoms. That is simply not true. The ancient Greeks merely proposed the idea that matter cannot be divided indefinitely, and there must be an indivisible amount of matter. The word atom, as a result, literally means indivisible. It was Amadeo Avogadro who first proposed and provided proof that matter is made of discrete entities. This idea was very advanced and radical for its time. This was a time without the technology we all take for granted. Advanced technology such as calculators and indoor plumbing. Some in the scientific community even called the idea crazy. Avogadro's law simply said that equal volumes of gases at the same temperature and pressure contain equal number of molecules. Avogadro's law does not say much. But one key word from his original statement started a revolution that gave rise to modern chemistry. That word is number, as in integer number. Before Avogadro, matter was considered to be fluid. The idea of matter being made of discrete entities changed all that. It was made clear that a transition to modern chemistry required us to think of matter, not in terms of its mass, but in terms of the number of constituent particles. During Avogadro's lifetime, the idea that there is an, as of yet undetermined, Avogadro's number remains just an idea. It was not until the turn of the 19th century that the first subatomic particle was first characterized. Depending on one's perspective, either 1919 or 1925 may be regarded as the moment when the proton was discovered. The name, proton, literally means first. We now know of two types of heavy subatomic particles, the proton and the neutron. These particles are the building blocks of the atomic nucleus. Thus we call them nucleons. We now know the rest mass of a proton is nearly the same as the rest mass of a neutron. The reason the term rest mass is used rather than just mass is beyond the scope of this presentation. It suffices to say, the average rest mass of a nucleon is 1.66 times 10 to the minus 24 grams. We also know of another subatomic particle, which is a building block of the atom. This is the electron. The rest mass of the electron is 9.11 times 10 to the minus 28 grams. If we take the ratio, rest mass of a nucleon to rest mass of an electron, we get 1822. Meaning the rest mass of an electron is less than 1 part per thousand of the rest mass of a nucleon. From this we can conclude that the mass of the atom is the same as the sum of the mass of its nucleons. The electrons do not provide a significant amount of mass. This does not make the electrons any less important. The electrons are the particles that, by virtue of their configuration, define the chemical reactivity of atoms. Now we have established that atoms are made of building blocks we call nucleons. We have also established that all nucleons are identical, and that means they all have the same mass. Now, suppose you have an atom, and this atom only has one nucleon. The mass of that atom would be equal to the mass of one nucleon. This mass would be 1.66 times 10 to the minus 24 grams. For an atom with 4 nucleons, the mass would be 4 times the mass of a nucleon, which is 6.64 times 10 to the minus 24 grams. For an atom with 12 nucleons, the mass would be 12 times the mass of a nucleon, which is 19.92 times 10 to the minus 24 grams. If this seems simple, it is not just your imagination, or me, pulling your leg. This is really how the masses of atoms can be computed. Since all atomic masses are the same mass times an integer number, we could take that common mass and give it a name. Atomic mass unit. AMU. We can also do something else. We can call this normalization. The quantity, 1.66 times 10 to the minus 24 grams, is declared to be equal to 1. Provided the label in this newly defined quantity is AMU, we could now simplify the masses of atoms by expressing the masses in units of AMU instead of grams. 1.66 times 10 to the minus 24 grams becomes 1 AMU. 6.64 times 10 to the minus 24 grams becomes 4 AMU. And 19.92 times 10 to the minus 24 grams becomes 12 AMU. The atom that weighs 1 AMU you might recognize as hydrogen 1. The atom that weighs 4 AMU is helium 4, and the atom that weighs 12 AMU is carbon 12. What we have here is called isotopic notation. The top number represents the mass number, which is equal to the sum of protons and neutrons. The two types of particles we call nucleons. The bottom number is equal to the number of protons. This is called the atomic number. For two atoms to be the same element, the bottom number must be the same, while the top number can be different. Two atoms with the same atomic number and different mass number are referred to as isotopes of the same element. Now the atomic masses would look neat if we were to write them up in a table. But there is a problem. The atomic masses are very small quantities. So small that a few million atoms would not register any mass in the milligram range. In order for the masses to start registering, we need to weight a very large number of atoms. How large would that number need to be? The atomic masses, when written in units of grams, give us a clue. All atomic masses are between 10 to the minus 23 and 10 to the minus 24 grams. That number would be between 10 to the 23 and 10 to the 24. But we can do better than that. We can choose a number such that the mass of that number of atoms, in grams, is numerically equivalent to the mass of one atom in AMU. You can try and do the math. You will see that, for example, there is a number such that the mass of one atom of carbon 12, which is 19.92 times 10 to the minus 24 grams, times that number, which we will call n subscript A, will give a mass of 12 grams. The number you would obtain if you do the math would be 6.022 times 10 to the 23. Remember, this is an integer number, but the number is too large to write in extended form, so we write it using scientific notation. This is the SI unit for amount of substance. 6.022 times 10 to the 23 is an integer number called the mol. We conclude that 6.022 times 10 to the 23 atoms whose atomic mass is x AMU will have a mass equal to x grams. For example, the atomic mass of the most stable isotope of polonium is 209 AMU. This means 1 mol, or 6.022 times 10 to the 23 atoms of polonium-209, weight 209 grams. Here are some questions to think about. Why do we use the mole? What is a mole equal to? Write out the number referred to as the mole in expanded form. Be warned that writing the mole in expanded form takes up a lot of space. Now we are ready to do some calculations. Suppose you have 3.00 moles of carbon dioxide, CO2. Compute the number of grams of carbon dioxide. Then compute the number of atoms in 3.00 moles of carbon dioxide. Remember that for stoichiometric calculations, the molar mass will be the conversion factor between moles and grams. Here we first need to obtain the molar mass for carbon dioxide. One carbon dioxide molecule contains one carbon atom and two oxygen atoms. If we look up in the periodic table, carbon has a molar mass of 12.01 grams per mol, and oxygen has a molar mass of 16.00 grams per mol. If we add up one carbon and two oxygens, we get 44.01 grams per mol. The molar mass of carbon dioxide is 44.01 grams per mol. Now we can, as we mentioned before, use the molar mass of carbon dioxide as a conversion factor between moles and grams. The molar mass is written as 44.01 grams of carbon dioxide per 1 mol of carbon dioxide. This way, the mol of carbon dioxide will cancel, and the calculation output will be in grams of carbon dioxide. Here we get that 3 moles of carbon dioxide weighs 132 grams. The next part of the question is simple to answer. You just need to remember that we are talking about integer numbers. We know that one carbon dioxide molecule contains one carbon atom and two oxygen atoms. That means each molecule of carbon dioxide contains 3 atoms. Because the mol is just an integer number, we conclude that 1 mol of carbon dioxide contains 3 moles of atoms. Now we just need to write the mol in numerical form. 6.022 times 10 to the 23. The answer is equal to 9 mol of atoms. In numerical form, that is 5.42 times 10 to the 24 atoms. Now we need to introduce the concept of an empirical formula. Take for example, sodium chloride. We know that the sodium to chloride ratio is 1:1. So we take NaCl as being the empirical formula of sodium chloride. Now consider the formula for hydrogen peroxide, H2O2. This is not an empirical formula, because the hydrogen to oxygen ratio can be simplified to be written as 1:1. We conclude that the molecular formula of hydrogen peroxide is H2O2. And the empirical formula of hydrogen peroxide is HO. You can try and figure out the empirical formulas of the compounds listed. These are molecular formulas, which are empirical formulas multiplied by an integer number. For example, propene belongs to a family of compounds that contain carbon and hydrogen in a 1:2 ratio. How can an empirical formula be determined from experiment? We can carry out a chemical reaction where a known mass of magnesium metal combines with oxygen in the air. Magnesium metal and its alloys are explosive hazards. They are highly flammable in their pure form when molten or in powder or in ribbon form. The bright light from burning magnesium contains ultraviolet radiation. When this experiment is done, it is best to avoid looking at the light. In this reaction, magnesium 0 gets oxidized to magnesium 2 plus, and oxygen 0 gets reduced to oxygen 2 minus. As we mentioned before, the electrons define the chemical reactivity of atoms. Electrons tend to move away from metals such as magnesium, and towards nonmetals such as oxygen. We can set up an example, using the kind of data you would get from such an experiment. Suppose you burn 0.135 grams of magnesium metal. Then you weigh the product, called magnesium oxide. Suppose the mass of the oxide is 0.224 grams. Given that information, we can confirm the empirical formula of magnesium oxide. We set up all the data, and we note that the mass of product is larger than the mass of the magnesium metal. The difference is the mass of the oxygen atoms that combined with the magnesium atoms. The mass of magnesium is 0.135 grams. The mass of magnesium oxide is 0.224 grams. The mass of the oxygen in the oxide is 0.089 grams. Now we set up the gram per mole calculations. For magnesium, we use the molar mass, 24.31 grams per mole. Written here as 1 mole of magnesium per 24.31 grams of magnesium. So that the grams of magnesium cancel, and the answer is 5.55 times 10 to the minus 3 mole of magnesium. For oxygen, we use the molar mass 16.00 grams per mole. Written here as 1 mole of oxygen per 16.00 grams of oxygen, so that the grams of oxygen cancel, and the answer is 5.56 times 10 to minus 3 mole of oxygen. The next step is what we call normalization. Here we take the ratio of the number of mole, using the smallest number as the divisor of both quotients. After doing this procedure, one of the quotients will always be equal to 1, while the others will be equal to 1 or larger. Here we have an instance where both quotients are equal to 1, after rounding off. Another rather simple experiment that can be carried out to find an empirical formula uses a type of compound called a hydrated salt. This is a type of compound with a specific number of water molecules bound to it. Some of these compounds change color depending on whether it has waters bound it or not. For example, cobalt chloride hexahydrate is color magenta. But if the water molecules come off, the resulting anhydrous cobalt chloride is blue. The reactant side of the chemical reaction equation has cobalt chloride H2O solid, to indicate 6 water molecules bound to each one cobalt chloride unit. The product side of the equation has the anhydrous cobalt chloride solid, plus the 6 water molecules in the gas phase. There is no simple way to predict how many water molecules will bind to a hydrate compound. The number must be empirically determined. Because the water molecules are loosely bound, only a small amount of heat is required to remove them. Hydrated salts follow a standard naming pattern. The first part of the name is the ionic salt, and the second part of the name is a prefix indicating the number of water molecules, followed by the word hydrate. For example, barium chloride dihydrate has 2 water molecules per empirical unit. Iron sulfate hexahydrate has 6 water molecules per empirical unit. Sodium carbonate decahydrate has 10 water molecules per empirical unit. Here, we have listed all other prefixes used in naming hydrated salts. As an example, suppose the mass of a hydrated salt is 43.69 grams and the mass of the anhydrous salt is 16.19 grams. It is good practice to write the chemical reaction equation. Here we can clearly see that the difference between the two given masses is equal to the mass of the water that evaporated. Doing the math gives 27.50 grams of water. As with all stoichiometric calculations, we need a molar mass. Here we obtain the molar mass of sodium carbonate by adding up 2 sodiums, 1 carbon, and 3 oxygens. The resulting molar mass is 106.0 grams per mol. Then we use the molar mass in the form 1 mol of sodium carbonate per 106.0 grams of sodium carbonate. So the grams of sodium carbonate cancel and the output is 0.1527 mol of sodium carbonate. We follow the same procedure with a 27.50 grams of water. We use the molar mass of water in the form 1 mol of H2O per 18.02 grams of H2O. So the grams of H2O cancel and the output is 1.526 mol of H2O. What follows is the usual normalization step, using the smallest number of mol as the divisor of both quotients. After rounding off, we get the formula for sodium carbonate decahydrate. A hydrated salt having 10 water molecules per empirical unit. For this next example, I have opted out of explaining the procedure because it follows from the previous example. I am also getting tired of typing on my voice synthesizer and I doubt anyone is paying attention at this point. For those of you who want to take a closer look, feel free to pause the video. We conclude this presentation with some questions to think about. What information do you need to determine a mol ratio? Can you get a mol ratio from percent by mass data? Write out the dehydration reaction equation for the hydrated salt copper 2 sulfate pentahydrate. For those of you who prefer the most interesting questions, you can try computing the percent water by mass in cobalt 2 chloride hexahydrate. You can pause the video and give it a try. Here is the answer. I did not think anyone would pause the video because there is very little honor left in this world.